This video is the third part of ISRO VSSC Technical Assistant Electronics Engineering previous year question paper with a detailed solution. The exam held on 2019. Up to question number 40 we discussed in the previous part 1 and part 2 videos. Just consider question number 41. A 100 watt power transistor having thermal resistance theta Jc of 1.5 degrees Celsius per watt and a maximum junction temperature specification of 150 degrees Celsius is mounted on a heat sink giving theta Ca value of 1 degree Celsius per watt. If the combination is used in an automobile control system where the ambient temperature can reach 75 degrees Celsius, what is the maximum power that the transistor can dissipate? Answer is option A, 30 watt. Power dissipation in package PD is Tj minus Ta divided by R of theta Ja, where Tj is the junction temperature. It is the highest operating temperature of the actual semiconductor in the electric device, and Ta is the ambient temperature. It refers to the temperature of the surrounding air or environment in which the device resides while the device is on. R theta Ja is the total internal resistance or junction to ampere thermal resistance. The unit is degree Celsius per watt. Which is the combination of theta Jc plus theta Ca plus theta Cs, where theta Jc is the transistor thermal resistance, which is the reciprocal of conductance. SI unit of a transistor thermal resistance is degree Kelvin per watt or degree Celsius per watt. Theta Ca heat sink equal to heat sink thermal resistance, which is the resistance that the heat energy meets as its flow from hot junction to cold junction. Aluminium alloys are the most common heat sink material. Theta Cs is insulator thermal resistance. It is resistance to that flow in insulator material and is sometimes referred to as R value. Higher theta Cs means more efficient the material is. Here given junction temperature Tj is 150 degrees Celsius, ambient temperature Ta is 75 degrees Celsius, and theta Ca is 1 degree Celsius per watt, and theta Jc is 1.5 degrees Celsius per watt. Substitute the given values in the equation 1, that is PD equal to PD equal to Tj minus Ta divided by R of theta Ja. That is PD equal to 150 minus 75 divided by 1 plus 1.5, which will we get 30 watt. Consider next question 42. The capacitance per unit length and characteristic impedance of a lossless transmission line are C and Z0 respectively. What is the velocity of travelling wave in the transmission line? Answer is option B, 1 by Z0 C. The phase velocity of a lossless transmission line is Vp equal to 1 by root Lc. The characteristic impedance of a transmission line is Z0 equal to root of L by C. Substitute equation 2 in 1, we get Vp equal to 1 by Z0 C. The next question is 43. What is the VSWR when feeding an RF signal to a 55 ohm load through a coaxial cable of characteristic impedance of 50 ohm? Answer is option D, 1.1. Given load impedance ZL equal to 55 ohm, characteristic impedance Z0 equal to 50 ohm. The reflection coefficient will be ZL minus Z0 divided by ZL plus Z0. That is 55 minus 50 divided by 55 plus 50, which is equal to 1 by 21. Now the voltage standing wave ratio equal to VSWR equal to 1 plus modulus of gamma divided by 1 minus modulus of gamma, that is reflection coefficient. 1 plus 1 by 21 divided by 1 minus 1 by 21, which is equal to 1.1. The next question is 44. The K-map given below represents the bit G2 for a 4-bit binary B4, B3, B2, B1 to gray G4, G3, G2, G1 converter. What will be the expression of G2? Grouping the variables in K-map. Grouping, consider the first grouping. Here the row wise B3 variable is not changing and column wise variable B2 bar is not changing. Consider the second grouping. Here row wise variable B3 bar is not changing and column wise B3 is not changing. Therefore the simplified expression of G2 equal to B3 B2 bar plus B3 bar B2, that is B3 XOR B2. A staircase light is controlled by two switches, one at the top of the stairs and the other at the bottom of the stairs, such that the light is on when and only when one of the switches is on and the other switch is off. What will be the logic equation in SOP form? Answer is option C, A bar B plus A B bar. Let the switch at the top of the stairs be labeled as A and switch at the bottom be labeled as B. Truth table for the required response is switch A, switch B, YA. 0, 0 means both are off. Then light is also off. 0, 1. Off, on means on. On, off means on. And on means off. The expression for the output is, this is the truth table of XOR gate. So, Y equal to A bar B plus AB bar. Question number 46. What can be the maximum clock frequency of a 10-bit ripple counter which will not cause a count to skip, considering 10 nanosecond propagation delay for each of the edge triggered flip-flops? Answer is option A, 10 MHz. We know that in ripple counter, the carry ripple through or propagate through every flip-flop. That is, the propagation delay for all the flip-flops are added to get the overall delay in the counter. For the counter to work properly, the next clock cycle must arrive when all the carries generated are propagated through all the flip-flops and the output is stable. This can be mathematically stated as, for the ripple counter to count properly, T clock should be greater than or equal to n into propagation delay time of flip-flop, where T clock is the clock interval. The maximum clock frequency F clock less than or equal to 1 by n into TPD of flip-flop. Here given that n equal to 10 bits and TPD of flip-flop is 10 nanoseconds. Substitute the values in this equation. F clock equal to less than or equal to 10 MHz. Calculate the fan out of a TTL circuit with the following specification. IOL maximum equal to 32 ampere, IIL maximum equal to 1.6 milliampere, IOX maximum equal to 400 microampere, IIH maximum equal to 10 microampere. Answer is option B, 20. This is a given values. Fan out high. Actually, fan out means it is the number of standard loads, that is input current of the driven gate, the output of a gate to the same logic family. Fan out high equal to IOH divided by IIH. Here substitute the values, we get fan out high equal to 40. And next one is fan out low, IOL divided by IAL. If we substitute the values, we will get 20. Effective fan out. Effective fan out is the minimum of fan out high and fan out low. That is minimum of 40, 20 is 20. In the given op-amp circuit, find the current I naught. The answer of question number 48 is option B, 0.5 milliampere. Applying KCL at node A. Using virtual ground concept, the potential at inverting terminal and non-inverting terminal must be virtually equal under the following condition. The op-amp must be ideal, that is the open loop given should be very high, ideally infinite. Negative feedback must be present. The input resistance of op-amp should be very high, ideally infinite, so that input current through both the terminal is 0. Here after applying KCL, we get 1 minus 0 divided by 10k plus V naught minus 0 divided by 100k equal to 0. After solving, we get V naught equal to minus 10 volt. Now the current will be I equal to 1 minus 0 divided by 10k, which is equal to minus 10 minus 0 by 100k. We will get I equal to 1 by 10 milliampere. Now applying KCL at node B, we get I equal to I naught plus IL. I equal to I naught plus V naught by 25K. I naught equal to, after rearranging, we get I naught equal to I minus V naught by 25K. After solving, we get I naught equal to 0.5 ampere. Question number 49. An amplifier operating from single plus 15 volt supply provides a 6 volt peak sine wave signal to 1 kilo ohm load. DC current drawn from the supply is 8 milliampere. What is the power dissipation in the amplifier? Answer is option C, 102 milliwatt. We know that electrical power P in a circuit is the rate at which energy is absorbed or produced within a circuit. A source of energy such as a voltage will produce or deliver power while the connected load absorbs it. The higher their value or rating in watts, the more electrical power they are likely to consume. We know that in this question given, amplifier supply voltage V equal to 15 volt, AC voltage Vm equal to 6 volt, DC current from supply I equal to 8 milliampere, RL load resistance is 1 kilo ohm, Vrms equal to Vm by root 2. Power delivered by the amplifier PT equal to V into I, that is 15 into 8, which is equal to 120 milliwatt. Power absorbed by the load is P absorbed equal to Vrms square divided by R, which is equal to 6 by root 2 whole square divided by 1 kilo ohm. The answer is 18 milliwatt. Hence, we need the dissipated power. By Telegon's theorem, power delivered by source equal to power absorbed by all elements. Therefore, power dissipated equal to total power minus power absorbed, which is equal to 120 milliwatt minus 18 milliwatt. The answer is 102 milliwatt. Question number 50. The reduction in gain of an RC coupled amplifier at a high frequency is caused by option B, internal capacitance of transistors. The inter-electrode or internal capacitance of a bipolar transistor is shown in figure. CBC, CBE, CE are the internal capacitance of BJT. The capacitor CBC between the base and collector connect output with the input. Because of this, negative feedback takes place in the circuit and gain decreases. The capacitance CBE offers a low input impedance at a higher frequency, thus reduces the effective input signal and so the gain falls. CCE provides a shunting effect at high frequencies in the output side and reduces the gain of the amplifier. The gain of a bipolar transistor is shown in figure. This is the graph between voltage gain and frequency in log scale. Consider question 51. Consider a voltage amplifier having a frequency response of the single pole low pass filter with a DC gain of 60 dB and a 3 dB frequency of 1000 Hz. Find its gain 1 MHz. Answer is option D, 0 dB. For all stable circuit and system, the product of gain and bandwidth is always constant. The gain in dB is represented as gain in dB equal to 20 log 10 of gain. Given gain 1 equal to 60 dB at 1000 Hz. 20 log 10 gain 1 equal to 60 dB. Therefore, gain 1 equal to 1000. Consider the case 1. At 1000 Hz, gain 1 into bandwidth, that is gain bandwidth product is 10 raised to 6. Case 2 at 1 MHz. Since the gain bandwidth product is always constant, we can write gain 2 into 1 MHz is equal to 10 raised to 6. Therefore, gain 2 equal to 1. Gain 2 in dB equal to 20 log 10 of 1 equal to 0 dB. Therefore, the gain at 1 MHz is 0 dB. Consider the question 52. The output voltage of a voltage amplifier is found to decrease by 20% when a load resistance of 1 kilo ohm is connected. What is the output resistance of the amplifier? The answer is option B, 250 ohm. Given that V0 decreased by 20% when RL is connected, therefore V0 dash is equal to new value of V0 when RL connected. V0 dash equal to V0 minus V0 into 20 by 100, which is equal to 0.80 V0, and the value of V0 equal to AV into VI where RL is not connected. Using the voltage division rule, we get V0 dash equal to RL by R0 R naught plus RL into AV into VIA. That is, we know the value of V naught dash equal to 0.80 V naught. Substitute the value here. 0.80 V naught equal to RL by RL plus R naught into we can write AV VI equal to V naught. By rearranging, we get RL plus R naught equal to RL by 0.80 V naught into V naught. That is 0.80 RL plus 0.80 R naught equal to RL. After solving, we get R naught equal to 250 ohm. Consider the question 53. Select the correct statement about a semiconductor. Out of the 4 options, option B is the correct answer. Electron mobility is more than hole mobility. Answer. The effective mass of the hole is greater than that of the electron. As the effective mass is less for electron, it moves faster than that of the holes. The relaxation times are often of the same order of magnitude for electron and holes. Therefore, they do not make too much difference. Find I and V in the given circuit assuming ideal diode. This is question number 54. Option C is the correct answer. 0 milliampere and minus 5 volt. An ideal diode acts as a short circuit when forward bias. That is, the diode can be replaced with a short terminal. Also, the diode acts as open circuit when reverse biased. That is, the diode can be replaced with an open circuit. Calculation here is, for the given circuit, the P terminal of the diode is at minus 5 volt potential and then N terminal is at 0 volt, that is ground. Therefore, the diode is clearly reverse biased. Replacing it with open circuit, the read-on circuit is shown here. So, I equal to 0 milliampere. Applying KVL from ground to minus 5 volt, we get 0 plus V minus 5 equal to 0. We get V equal to 5 volt. Question number 55. What will be the modulation index of an amplitude modulator if carrier signal has amplitude of 100 volt and frequency 1 MHz, whereas modulating signal has amplitude of 20 volt and frequency 10 kHz? Answer is option C, 0.2. Before that, for an amplitude modulated system, the modulation index mu equal to AM by AC, where AM is the message signal amplitude and AC is the carrier amplitude. The modulation index of an amplitude modulated wave is independent of the carrier and the modulating signal frequency. Since the modulation index is related to the carrier amplitude through an inverse relationship, we conclude that the plot of modulation index versus carrier amplitude will result in a hyperbola. Here given AM equal to 20 volt, AC equal to 100 volt. Therefore, the modulation index of amplitude modulated system mu equal to AM by AC, which we will get 0.2. Question number 56. Calculate the maximum value of RS in the given circuit to give 12 volt regulated output from an unregulated supply of 28 volt for a maximum load current of 150 milliampere. Zener voltage is 12 volt and knee current of Zener diode is 10 milliampere. The answer is option D, 100 ohm. Actually, Zener diode is used for voltage regulation application. And it is operating in reverse biased condition. Zener diode is made by highly doped semiconductor material. Operate on the principle of the tunneling effect. Here given VZ equal to, that is Zener voltage is 12 volt, knee current IK equal to 10 milliampere, load current IL equal to 150 milliampere, regulated output voltage VL equal to 12 volt. Consider the circuit and applying KCL at node A. IS equal to IK plus IL, which will get 160 milliampere. Applying KVL in loop 1, we get 28 minus ISRS minus VZ equal to 0. After rearranging, we will get RS equal to 100 ohm. The maximum value of RS in the circuit will be 100 ohm. Question number 57. What is the minimum PIV required for a diode used in a full wave rectifier circuit using a center tapped transformer with a secondary voltage of 50 volt 50 volt RMS? Option A is the correct answer, 141.4 volt. In a full wave rectifier using center tapped transformer, minimum PIV rating for a diode is PIV equal to 2 Vm. which we know VRMS equal to Vm by root 2. Therefore, PIV equal to 2 root 2 VRMS. Given VRMS is 50 volt, therefore PIV equal to 2 root 2 into 50 volt. That is 100 root 2. 100 into 1.414 equal to 141.4 volt. Question number 58. Identify the gate realized by the MOSFET circuit shown in figure. Option B is the answer, NAND gate. CMOS logic circuit is an extension of CMOS inverter. It consists of two network transistors. A pull-down network PDN constructed of an NMOS and a pull-up network PUN constructed of PMOS. PDN, since NMOS conduct when the signal gate is high and PDN is activated when the inputs are high. PUN, pull up network, it comprises of PMOS and conduct when the signal gate is low. The PDN and PUN are connected in parallel to form OR logic function. They are connected in series to form AND logic function. The output expression of the given circuit Y equal to A B bar. Therefore, the gate realized is NAND gate. Question number 59. Differentiate A cos cube t with respect to A sin cube t. Answer is minus cot t. We know that dx by dy equal to A cos cube t divided by A cos square t. Consider x equal to A cos cube t and y equal to A sin cube t. Dx by dt equal to differentiate A cos cube t with respect to t. That is minus 3a cos square t sin t, and dy by dt equal to 3a sin square t by cos t. We need dx by dy. So, divide dx by dt to divide dy by dt. We get answer of minus cos t by sin t, which is equal to minus cot t. The last question of this video is 60. Which of the following advantages are there for a Darlington pair compared with single transistor? The answer is option A, 1 and 2. High current gain and high input resistance. A Darlington pair is a two-transistor circuit with the emitter of transistor is connected to the base of other transistors, while both collector terminals are connected to the common terminal. Symbolic diagram of Darlington pair is shown here. It has high current gain beta equal to the product of current gain of individual transistors, and is useful in application where current amplification or switching is required. It also has high input impedance and low output impedance. The current gain of Darlington pair in common emitter configuration is approximate beta square. Thank you.